Good morning, everyone, and welcome to another cup of cosmic coffee. Speaking right now is Danielle Adams. I'm the Deputy Director for Marketing and Communications here at Lowell Observatory. And you see on the screen there Dr. Jeff Hall, who is the Director of Lowell Observatory. And today we're going to tag team a bit and introduce you all to the inner workings of the Lowell Discovery Telescope, our 4.3 meter flagship telescope that is located about an hour away from Flagstaff. Jeff, take it away.
Okay, thanks, Danielle, and hi, everybody. It's great to be with you for another episode of Cosmic Coffee. We've got something a little different for you this morning. I think it should be a lot of fun. As you can see, I'm outside here at the site of the LDT, the Lowell Discovery Telescope. And just a couple of logistical notes before we start today's show. We're going to be walking around the site a bit. If the audio and the video drop out for 10 or 15 seconds, it's because my iPhone is switching at a couple of networks out here. And then the other thing to note is I'm out here and I'm broadcasting back to Flagstaff, 40 miles away. And Danielle is collecting my Zoom call and then broadcasting it out to YouTube to all of you. So you can type in questions to the YouTube chat, and Danielle and I will sort of tag team to try to answer them. Danielle, for a start, why don't you give everybody an overview of where we are with some of that drone footage we've got?
Awesome. So you're looking now at some aerial footage generously donated to us by Corvid Aerial Solutions right here in Flagstaff. And this is showing a nice view of the Lowell Discovery Telescope dome as we orbit the dome a bit slowly here. You can see now coming into view is the very large shutter on top of the dome, and those horizontal bits sticking out in either direction are the rails along which the shutters open. All right, back to you, Jeff.
Okay, thanks, Danielle. And so now we will, I'll give you a view of what you just saw from the air. Let me switch my phone here. And first of all, I'll have to apologize for the terrible view we have here at 7,800 feet elevation. As Danielle said, about 40 miles south of Flagstaff, we're overlooking what we call the Mogollon Rim here in Arizona, the very southern extent of the enormous Colorado Plateau that makes up the high country of northern Arizona and Utah, western Colorado, and a bit of New Mexico. You can see on a day like this why astronomers have a proclivity for putting observatories in Arizona. Look at this sky. It's just magnificent. Now we're going to go around this way, and here's the dome of the telescope. Some of the shutters open. You saw that just before there at the top. You can see the big I-beam with the shutter. This is about 7 stories here, and we're going to work our way up through that. If you look carefully, and right between those 2 trees there, you can see the San Francisco Peaks, and that's all of us here in Flagstaff call that home. Those are the mountains just north of town. And then over here is the Diane Blackett and Robert Walks Telescope Support Building, so named thanks to a magnificent gift from Diane and Robert. And we're going to start there. And so I'm going to walk over there and let you know what that building is for. So first of all, I'm going to take a flying leap here. Standing on this giant mass simulator that's shaking down the telescope. Right here, you can see this cart. This is the mirror transport cart that transports our mirror cell from the main building over to the auxiliary building on these railroad tracks when it is time to replace the aluminum coating on the mirror. That's a process that takes about 6 weeks, and it's rather heart-stopping. I'm glad we don't have to do it more than once every 5 or 6 years. So we're going to walk into this building. And this is the auxiliary support building. I'm going to switch the camera around to give you a sense of scale here. There we go. So this big tank right here is the tank we use to re-illuminize the telescope mirror, the primary mirror. It pops up right here at, let's see, right here at this seal. put the mirror in there, pump it down to a vacuum, and that's how we replace the aluminum coating every 5 or 6 years. To actually put the new coating on the mirror takes just a couple of minutes, but the whole process of getting the mirror out of the telescope and putting it back in takes about 6 weeks. And when we get up to the observing floor of the telescope dome, you will see why. It's a very complex facility. This was a conscious decision on our part. Obviously, it increased the price tag to build something like this, but having the ability to recoat our mirrors on site makes a lot more sense in the long run than having to ship them off to Tucson or some other place that could do it for us. So we're very fortunate to have this building. And now what we're going to do is switch over to the main building. There are some other folks here today, so we are going to do the responsible COVID era thing and put on this very stylish mask. So there, and I think I'll just complete the look. Now, how's that? That is a look, is it not?
Looking great, Jeff.
Yeah, thank you. I'm styling this stuff. All right. So I'm going to flip the camera now. Okay, and there may be a dropout as I switch buildings because we're going to be changing from one network to the other. So what we're doing is walking down the railroad tracks into the receiving bay. So I'm right below the dome now. Some nice geometry here. And these tracks are where the mirror is lowered down. Oh, here's Jake. Hi, Jake. This is Jake Teagues, one of the DCT engineers. Well, be seeing you around. So they're getting ready this morning to do a wash of the primary mirror. Cool. All right, awesome. So we are out here on a regular work day. There's at any given day, there will be 3 or 4 engineers here taking care of the telescope during the day before observations start at night. So right up there on the second floor, you can see the base of the telescope itself. You getting all this okay, Danielle?
Yeah, absolutely. And just for context, do you have a sense of how much all of this weighs?
I do indeed. So the telescope begins at that blue pedestal right there in the middle of my view right now. And everything from that pedestal up to the top is about 135 tons.
Wow.
So pretty massive. And you can see 2 elements up there that are 2 of the azimuth motors. And we'll talk about those a bit more when we get up to the mezzanine level there. One other thing I want to show you here on the bottom, this circular central portion here is the pier. And so this is what the telescope sits on.
Yeah, we're losing you a little bit there, Jeff.
And power. Yeah, okay. That's because I just went inside a giant concrete bunker. So it's probably bad for the signal. Have you got me now?
Yep. Yeah, that looked like a good Faraday cage for sure.
Yeah. So this supports the whole telescope. And one thing you can see right there is a squishy seal. And that's because they're separate buildings. The telescope is completely mechanically isolated in order to minimize any sort of shake and vibration getting to the telescope, say from the wind blowing against the outside dome. Okay, so now we're going to work our way around the circular first floor. There's 3 floors here. Right back here. Inside this room, some of you on some of our shows have heard from Dr. Joe Lama about the Express project, searching for Earths around other suns. And that instrument lives right in this room. And this giant computer rack right here is part of the system that controls the calibration unit for that project. You have to calibrate that thing exquisitely carefully. So now we work our way on through. In here, you can see the computer room. Every control system associated with the LDT has its own computer control. And so that's all stored here in this room. You can see on this display where the telescope is pointed. Currently pointed straight at zenith because they're just getting ready to start working on it for the day. And then in here, the control room. And this is where the telescope operators and the astronomers work at night. So over here is the station where the TO, the telescope operator, will sit and operate the telescope. And the principal job of the telescope operator is to protect the telescope from the astronomers who sit over here working on the instruments and collecting the scientific data for the evening. And the exact sort of data we're collecting depends on the project we're doing. You can see on the wall. Yeah, Daniel?
When you say that, Jeff, protect the telescope from the astronomers. Now, how much, mayhem really could an observer cause?
Not much. That's one of our running jokes. And we're fortunate to have just an outstanding crew of TOs who do a great job operating the telescope. So maybe this would be a good time to tell you a little bit about some of the features and actually the name of the telescope, Lowell Discovery Telescope, or LDT. Until recently, it was called the Discovery Channel Telescope. Those of you who are familiar with the project probably know that. This $53 million facility was built partly thanks to very generous contribution from Discovery and their founder, John Hendricks, eventually totaling a $16 million contribution to the project. And so that was the original name of the telescope. We recently renamed it in collaboration with Discovery to emphasize the fact that this is entirely a Lowell Observatory owned and operated facility, as well as to reflect the fact that Discovery these days is a lot more than the channel, and we work with them in a number of conduits other than just the channel. So I think that was a good step forward for both of us. Okay, I'm going to turn this back around now. And what we're going to do at this point is head up to the mezzanine level. So right over here, of course, the small kitchen. Yes, the critical element that keeps the lifeblood of any observatory moving along late at night. So here we go into the lobby, and we're going to go up one flight of stairs to the mezzanine level. And so, here we're going to do our Blair telescope project kind of thing as we head up the stairs.
So how many stories are you climbing up right now?
I went up one story, just there. I really hope I don't drop my phone right now because that would put an abrupt end to the show. So we're going to go through here, and now you can see where we are. We're one story up. We were just down there on the receiving bay. Now we're up here. We'll come in through this pinch point. Here's the big telescope yoke right here. And just a couple of things to point out on this level. First of all, our ventilation system. I'm going to go over and, oops, wrong one. Let's do this one. So one of the basic ideas behind an observatory is you want the conditions inside the dome to be the same as the conditions outside the dome. And so we use these doors to allow air to flow through and equilibrate the temperature. See this gorgeous view, again, looking out over the rim from here. Now we can come back in, and you'll see these are the two azimuth motors for the telescope. Okay, they drive the telescope in. You can see it's sitting on this pedestal. There's this giant azimuth gear right there, liberally gooped up with grease. And this rotates the telescope in sort of the horizontal axis, the azimuth axis. Okay, oh, and here's Frank Cornelius, one of our engineers. Hi, Frank, you're live. And you can see the whole thing is mounted on this giant bolt pattern right here, this gray part. That is the very top of the pier we saw down below when we went down into the bunker. This had to be very precisely engineered to be absolutely flat, because you can imagine if this is a little bit canted one way or the other, that's a permanent set of errors into any point the telescope makes. So the guys building this were doing this with lasers up here to make sure everything was aligned. You can the yoke here is partitioned and honeycombed to allow airflow and for good thermal control of the whole structure, and that gets vented out here and then out through the doors when we're open at night observing. So there's a huge amount of attention in this facility to managing the thermal properties of the telescope, and that is critical to the smooth operation of the facility. Okay,
So
Yeah,
Jeff, we have a couple questions coming in here.
sure.
One relates to whether astronomers are observing remotely or on site, and of course, we've changed procedures in response to the coronavirus. So perhaps you could elaborate on that.
Right. We actually have had the capacity to observe remotely for quite some time. And right now we are only observing remotely because of the coronavirus. And we want to minimize personal interactions as much as we can. So yeah, observers from our partners at Boston University and the University of Maryland regularly use this telescope from their offices in Hawaii. And increasingly remote observing is becoming standard practice for many facilities.
Great. And then we had a second question come in about security for the Lowell Discovery Telescope.
Right. It's just what are our security measures?
Yeah, and the physical security for it.
Yeah. So obviously we have a automated security system in both buildings. You can see the site is completely surrounded by a fence. Actually, I can take you out this way. This is a really nice view out this door. This is emergency. I'm going to try not to get trapped out here because that would also make the rest of the show fairly boring. So we'll try. So, there's our automated gate. We have security cameras on the whole thing. And as you can see, we're not right in the middle of an urban area here. So there's not that much activity, and it's a pretty secure site. Everything you see here is actually the Coconino National Forest. So we are operating this site on a 35-acre special use permit. It's been great. The Forest Service has been a great partner in helping us make all this happen.
Great. And then another question has just come in. What's the current temperature there, and how quickly does the telescope stabilize after sunset?
It's a good question. It stabilizes quite quickly, and the engineers, astronomers would probably have the better number than I, but we've put a number of design features into the telescope to allow it to stabilize quickly. I would say right now it's probably about 75 out here. I think the forecast high today is about 85, which is quite warm for this elevation.
Great.
So we'll talk about some of those thermal features when we get upstairs, which we will do now. We'll go up and see the business under the telescope. So now I'm going up one more story. Okay, so we are streaming out live to YouTube and just showing all our visitors a little bit about the LDT. So here we are on the observing floor. You can see more ventilating doors there to let air pass through the dome. And here we go. Here's the blue yoke. This is the mirror cell back here. And then on upward to the support structure for the secondary mirror. So let me tell you quickly how this optical system works. Right up there at the top, right in the middle of the view now, you can see the secondary mirror. It's about 1.4 meters. And what happens is light comes in through this open shutter. When it's open, it comes down to the primary mirror of the telescope, which is right in there. Those are some of the supports for the primary that you're seeing. Bounces back up to the secondary, back through a hole in the center of the primary to the instrument cube, right here on the business end of the telescope. And all of our instruments are mounted here. We'll circle around to the other side in a minute, and I'll give you a quick overview of what those are. But there was a question before about thermal characteristics. You look really carefully. It's a little hard to see these silver, those 1, 2, 3, 4, 5, 6 silver housings you can see are part of the support system for the telescope mirror. And you can see little push rods sticking in there, attaching to the mirror. And the mirror is only 4 inches thick. And it's called a thin meniscus design. And the reason for that is to allow it to maintain steady equilibrium with the outdoor surroundings as things heat up and cool down from day to night. On the back, you can see more of these support rods. Here's one right here. This is what we call the active optics system of the telescope. And I'll describe just that one. There's so many subsystems here. This show could easily go 2 or 3 hours to talk about them all. But what happens is this mirror is so thin that it actually deforms under its own weight as the telescope moves from one part of the sky to another. So all of these push rods are computer controlled, and they push it back into shape with exquisitely small amounts of force being applied to the mirror. And this is one of the things the telescope operators watch throughout the night as the telescope is in use and as the astronomers are asking them to go to different parts of the sky. They will make sure that this system is tuned up and the mirror is in shape. Now, right up here, I'll come around to the side. You can see here, this is the elevation motor system there. So the telescope now is pointed at zenith. It can slew down almost to the horizon. Okay. And so it's not, this is what we call an alt-az or altitude azimuth mount. Unlike an equatorial mount, which you see for a lot of off-the-shelf telescopes, they're mounted in an angle, so they're pointed at the North Star. This telescope is mounted straight up and down on its big pier, and there's good engineering reasons to do that. You can imagine you wouldn't want something like this having to be canted off at some weird angle. It would just be a nightmare of construction and expense. One of the complications, though, is a telescope like this, as it tracks an object, the sky is rotating, and the star field will rotate, and your images will get smeared. And so that is what this gear right here is for. Here's this huge gear. That's the image derotator. This whole instrument cube rotates counter to the field rotation as the telescope tracks. So just another layer of complexity. Now we'll come around here.
And Jeff, as you're going around to that side,
Yep.
Let's break away a moment. And we've got a really nice time-lapse video from a fellow astronomer at NAU, Dr. Stephen Tegler. And we'll take a look here at what the
Awesome.
LDT looks like in motion.
Excellent. Let's do it.
And so you can see, of course, this is rather sped up, but you can see the telescope moving in both axes. And I'll just run that one more time because that was pretty brief there. So you see it going vertical. We've got the mirror opening, the covers opening, and then it rotating. All right. And Jeff, as we go back to you, we've had some more questions come in. One was about the effects of light pollution from Phoenix, and we can hit that just a bit later as we do have some nice nighttime time-lapse videos
Sounds
as
good.
well. Keith Helinsky asks, does maintenance happen daily? Things like greasing the azimuth gears and whatnot.
So yeah, maintenance is ongoing. See, one of our engineers is out here right now. Actually, we have several out here. They're actually going to be washing the mirror later today. They do that. Frank, how often do we do the aqueous wash? Twice a year. Okay. Okay. Yeah. Okay. So there's some maintenance things that happen several times a year. Other things that have to happen, people are out here daily. Maybe something happened the night before. So there's an error report and the maintenance crew will come out. And then major operations like re-illuminizing the mirror. When we have to do that, remember I said earlier in the show that takes about 6 weeks. So right here, you can see a dividing line between a slightly darker gray and lighter gray below. Okay, the lighter gray there is the start of the mirror cell. The whole mirror cell, instrument suite, and the mirror itself weighs about 27,000 pounds, and it all has to get removed, and everything you see has to get unplugged. And as you can imagine, it's really helpful if everything gets plugged back in the same spot. So you got to do this really carefully, and it just takes a long time. And fortunately, our engineers are incredibly meticulous and have done this extremely well thus far. I want to show you, just going back quickly to the active optic system, Right in there, you can see one of the axial supports. There's 120 of these that our 6,700-pound mirror sits on. And now I'm going to put myself at horrendous risk and climb a little bit up this ladder. And there you can see a few of the 36 lateral supports, and you can see those rods that are attached to the mirror. And these are really helping prevent it slide out of center in the mirror cell. Because you can imagine as this telescope tips down and points toward the horizon, you've got over 3 tons of mirror that wants to sort of slide to the bottom. So that's supporting it. Now, right down here, we're going to go in underneath and take a look at our instrument cube. This was designed and built entirely by our wonderful crew here at Lowell Observatory. Our instrument scientist, Tom Vita, was one of the leads on this. And the beauty of this thing is it's this giant cube. So you can put 5 instruments on it at once. And indeed we have. Right down here is the primary imaging camera, the large monolithic imager. This thing right down there is part of the system that cools the detector down to a suitable operating temperature. This right here is the Devaney spectrograph, an optical spectrograph on permanent loan from the good folks at Kit Peak. Then on the other side, let's see, what have we got? Where's Express? I'm trying to find all the fibers. I'm not seeing them. Over here is an infrared spectrograph called NITES. So at this point, we've got the instrument cube fully populated out with imagers and spectrographs observing in different parts of the spectrum, both the optical and the infrared. And inside the cube here are deployable mirrors that we can slide back and forth, enabling us to change instruments within about a minute. And that makes this telescope extremely powerful and versatile for carrying out long-term programs that require frequent instrument switches. In other words, instead of just 2 nights a month, maybe you need a quarter of a night, 8 nights a month. And we have some programs like that. Or if something unexpected happens, you can switch very quickly and go and get an observation of it.
So how does that compare to other professional telescopes of this scale in terms of being able to change out instruments?
So that capacity is not unique. There are other telescopes that are outfitted like that. But one of the real strong advantages of this telescope is it's all ours. It is, 4 meters aperture is not enormous by the standards of the largest optical telescopes, which are these days in the 8 to 11 meter class. There's some 30 meter class instruments planned and being developed. But it's unusual for one institution to own it all by itself. And that gives us the ability to do the kinds of programs that have been Lowell's bread and butter for so long, such as scanning the sky to search for a planet, or like my own research to follow the activity cycles of stars. We have astronomers who have spent years surveying the sky for near-Earth asteroids, or we want to characterize the properties of a huge sample of teensy little galaxies. And all of this takes lots of observing time over weeks, months, even years. And that is a unique strength of Lowell Observatory. So let me wrap up here, and then we'll go back outside so I can lose this somewhat suffocating mask. And I'll tell you a little bit about the dome. You can see the dome construction here. It's not a hemisphere, it's angular. That was an evolution in the design process that actually worked out very well for us. We have this giant crane, the yellow thing up there. That gets its principal work out when we have to take the mirror out of the telescope to reilluminize it. Then over here, there's 4 of these things around the dome. These are the motors. There's another one right over there that rotate the whole dome. And right here on the main dome rail, you can see our grocery checkout solution to encoding the dome. It's got these little barcodes at 1 degree increments that we read with a little laser. And so wherever the telescope goes, so also goes the dome. Now we're here. This is our flagship telescope. Will be for the next several decades. And you know, our other flagship telescope is now like 125 years old, and that's the old Clark telescope back on Mars Hill. I think one thing that's kind of cool, if you look here, this is the dome motor, and what it does is it turns and drives right under here this incredibly high-tech tire, which is butted up against that rail, and the friction of these four tires against the rail helps the dome rotate. Now, you can go back to the Clark telescope on Mars Hill and see that it's mounted on, guess what? Tires.
Yes.
They've tried different things over the years, but basically we use tires, and they actually have a very similar aspect to the ones that we're using here at DCT. So I think if old Percival Lowell were to come out to the DCT site, he'd at least see one thing that he would think was pretty familiar.
So before you continue on further, we've got a nice video taken by Stephen Levine of the opening procedure at the LDT. And so we're going to run that now. And what you're seeing on the screen here is just over there on the left, you can see light coming into the dome as this opens, and this is shown here at 5 times real time. It takes almost 3 minutes just for the shutter that you see to open in real time. And then as that finishes, then you'll see it getting brighter inside. This is from opening the various shutters around the dome, which facilitate airflow. And then now you see some dark triangles opening up. These are the mirror covers. There are 4 of them. And then you can see the LDT rotating and aligning itself up with the open slit. And then we also have a really nice view at nighttime from our friend Harun Mehmedinovic from the Sky Globe project. And here you can see a time lapse at night of the LDT aiming at different targets and tracking them through the night. The many colors at the back are colors for the different instruments on the instrument cubes. And Jeff, this relates to another question that's come in. How many total instrument packages have been developed so far for the LDT?
Okay, let's see. So are you still on a video, or are you back on me?
No, I'm back on you.
Okay, and as you can see, we're back outside, back kind of where we started, looking up at the dome there. So we've got 5 instruments on now. There's another instrument from the University of Maryland on development. So yeah, we're up to 6 or 7 total instrument packages that have been developed for the telescope, and it's only within the last year we've gotten that cube completely populated, which is great to see.
And then we've also had loaned instruments that have temporarily visited the LDT, like iGrins.
Right. So that was a high-resolution infrared spectrograph, which was a joint project of the University of Texas and the Korea Astronomy and Space Science Institute that had sort of a rotating presence here. And the amount of science that came out of that was incredible. So yeah, we can accommodate visiting instruments as well as develop our own.
Excellent.
So you said there was a question about light pollution?
Yes. Yeah, there was a question. Is there any effect from light pollution from Phoenix?
We can certainly see it. So if I go this way, let's see. So Phoenix is a little more, probably about center screen right here, 90 miles, roughly that direction. And you can definitely see the light dome. And it's not to the point that it really interferes with a lot of observations, but it is growing, and it's growing to the north. Fortunately, Closer in, right here in front of the very distant mountains, is the Verde Valley. And several of the communities in the Verde Valley have, like Flagstaff, recently acquired International Dark Sky City status. And so we're very happy and pleased to see a lot of interest from our neighbors in the Verde Valley to preserving the really beautiful skies that we have here. This is one reason we picked this site. We took about a year to figure out to come here back in 2003 and 2004, because if you're going to plunk down $53 million, you want to be reasonably sure you're putting it in the right place. Stidman had a great combination of very dark skies and a very stable atmosphere, a minimal amount of what astronomers call seeing, or atmospheric turbulence that degrades the images. It's kind of a pity. Starlight comes, however many trillions of miles to the galaxy in or less a pencil beam, and then in the last 50, just because of Earth's atmosphere, we like to find a spot where there's a minimum amount of which is the sort of the technical term for what's going on here.
And we've got some nighttime time-lapse videos. I'll show them together. Cool. Here. You can see a slight bit of light pollution on the lower left corner from this first one. But overall, the sky is just really gorgeous. And then we'll show another one here that's a little bit closer view, looking right up against the telescope into the night sky. And as we're looking at this, we've got some more questions that have come in, Jeff. And one question is, why is it preferable to recoat the aluminum on a regular basis versus adding a protective coating like silicon dioxide?
Well, actually, the top. Well, first of all, you don't want anything between your reflecting surface and your detectors that would destroy your image quality and the quality of your observations. The top layer of atoms in the aluminum coat does actually create a protective layer of its own, so aluminum oxide on the top of the mirror. But the coating is extremely thin. It's only about 1,000 angstroms thick. So we literally deposit the aluminum on the mirror atom by atom. And the reason for that is the surface of that mirror is so exquisitely figured to get maximum image quality. It's precise down to about 50 to 75 nanometers. So you can't just slather aluminum on it. You've got to have an absolutely uniform coat. And that's what the role of that high-tech tank in there is. But because that coating is so thin, and stuff happens over the years, that it wears off. You have particles, dust collects on it. As Frank was saying upstairs, every couple times a year we wash it in place. But eventually, there's really nothing to do but take the mirror out entirely, strip off the old degraded coat, and put on the new one. And you can really see the performance hit if you measure the throughput of the telescope over time. It will gradually degrade. And if it's degrading, that effectively means you got a smaller and smaller telescope. So you just need to redo that. And it's a little heart-stopping to pull a $7 million piece of glass out of there, but it's got to be done.
And how often is the mirror recoated altogether?
Happily, only once every 5 to 6 years. The coating seems to last pretty well.
And then the wash happens a few times a year.
Yeah, twice in the spring and the fall.
Yeah. Okay, and then we have another question. What percentage of the night sky can be seen? So, obviously we have, a slit, and then of course that rotates with the telescope. But, is there any blockages in the night sky?
So the principal blockage is the horizon. And so here in Flagstaff, we are at latitude 35 degrees north. And that means right over here on the southern horizon, farthest we can see is 55 degrees south. And I can't do the trig in my head, but I'm going to guess that's probably, 80% or so of the entire sky, most of it. Otherwise, not only do observatories like to be in very clear, dark place, they like to. So here we are at 7,800 feet with just spectacular horizons everywhere, and in particular to the south. Because like I said at the start of the show, right over here is the Mogollon Rim. It's kind of this giant 200-mile cliff that runs across Arizona, and it drops off just to the south of here, leading to the northern region, is the Sonoran Desert. So we southern horizon. Now that said, anything farther than a declination of about 55 south is invisible from here. So we do have astronomers who regularly travel to sites in the southern hemisphere, like our astronomer Phil Massey regularly goes down there to observe the Magellanic Clouds, the satellite galaxies of the Milky Way, because you just can't see them from here. They never get above the horizon.
All right. Now, we'll be wrapping up this broadcast in about 5 minutes or so. If you're viewing this now live, feel free to ask any questions that may still be burning on your mind. We do have a question from Haley Osborne. And
Hi, Haley.
She asks, do you use the LDT for any of your own research?
So far, no. Being the director, I don't have all that much time to do research anymore. However, when we were walking through the facility, I showed you the Express spectrograph, and I actually have gone in on a proposal to NSF research proposal with another one of our faculty, because that Express is it's exactly the same kind of spectrograph I've been using for 25 years to study the activity cycles of the sun and stars, except completely on steroids. This is just a whole new level of precision and resolution that makes our plucky old spectrograph pretty much obsolete. So yeah, it'll be nice to be able to hopefully divert a little bit of time into continuing to study the variations of the stars with this instrument. And I do want to say before we sign off, that we are so incredibly thrilled with how well this telescope developed and how well it works, which
we lost you a moment there, Jeff.
Our very own engineer. Okay, where'd you lose me? Have you got me now?
Yep.
All right, where did I drop out?
Just a few seconds back.
Okay, so I was just about to say this telescope works phenomenally well. It is very stable. I talked about the system that keeps the mirror's shape in the right figure. And there are a couple of ways you can use that system. One is more ongoing and involved than the other. It really maintains its shape very well as we slew back and forth between similar positions, and it points tremendously well. You can imagine if you slew and you're looking for a star and there's nothing in the field, you could waste a huge amount of time hunting for your target. Some telescopes have poor pointing. This points like a dream. And so for programs like the one I was talking about, where you're doing lots of relatively bright stars and just ticking them off one by one, the efficiency of this instrument is tremendous. And so I think all of our faculty and all of our partners agree it is one of the, if not the best performing 4-meter telescopes they've ever used anywhere in the world. And needless to say, we are incredibly proud of that. And it's going to be fabulous to see all the research it's going to do over the rest of its lifetime.
It's absolutely an amazing instrument. I get goosebumps every time I go to the LDT
me too.
And take a look at it for myself. We got a couple more questions that have come in. One says, what do I have to do to work at Lowell Observatory as an engineer? I know we do have job postings from time to time, even jobs that work right here at the LDT.
Yep. The simple answer to that is watch the employment page on our website. All the positions that come open are posted there. And in fact, there will be some. We're out here at Happy Jack Ranger Station, near the Happy Jack Ranger Station at the LDT site. About 25 miles back up the road is our other dark sky site at Anderson Mesa. That's about 10 miles outside of Flagstaff. one of the facilities out there is the Navy Precision Optical Interferometer, and we've recently received a very substantial amount of funding to do quite a few upgrades to that facility, and there will absolutely be engineering positions available. We're a little bit constrained right now because of the COVID crisis. Obviously that's putting a lot of financial strain on us, but where we have projects where there is external funding to come in and build our capacity and upgrade our instruments, fine. So we will definitely be making some hires on that front. So keep watching the website. We love to have smart people come work for us.
Great. And then what will be our final question then is there any push for Phoenix to go dark skies or to become a dark sky city?
Yeah, the answer is yes. The question is how you do that in a metro of 4 million people. I don't necessarily see Phoenix itself doing that, but Fountain Hills, right on the outskirts of the Phoenix metro, one of the cities right there in the northeast, is an IDA dark sky community. And that's really the incredibly smart thing the IDA has done with that program. To be a dark sky city, you don't have to have a dark sky. You just have to have a commitment within your community borders to best lighting practices and ongoing education for citizens and visitors about the virtues of dark skies. So with Fountain Hills having done that, I've given a talk down at Cave Creek and Carefree. Some of the other towns are now looking at that. And so I think as we approach dark sky protection in large metros, this is one way to do it, is start at the community level. Even Phoenix itself, it is very light polluted. They have been, like so many communities, switching out their outdoor lighting from legacy, gas discharge systems to LED. Dark sky advocates down there really went to council and city staff and urged them to use the lower temperature white LEDs, which are less light polluting. Now, even better than that would be various flavors of amber LEDs, which is what we will be using here in Flagstaff. But certainly, the Phoenix City Council did the right thing by using, somewhat less dark sky damaging white LEDs than many other communities are doing. So it's an ongoing thing, and we always enjoy heading down there when we're allowed to travel to work on these issues and preserve Arizona's dark skies, not only for us here in the north, but the huge critical mass of observatories all around Tucson also depend on maintenance of the quality of our skies. Arizona is truly one of the astronomy capitals of the world. It's a multi-billion-dollar industry here in the state, and very much worth preserving.
Great. Now, I guess a final question from me, as this series is called Cosmic Coffee. This morning, I'm drinking a rather nice dark roast from Stronghold Coffee. What were you drinking this morning?
Yeah, and I was driving out to the site, so I actually ended up on a repeat, just swinging by the little kiosk there at Matador.
Awesome. We'd really love to give props to our local coffee houses here in Flagstaff, and really hope everyone is on the road to recovery.
Absolutely.
Great. Well, any last words for us from the LDT?
Not just that. Wish I could just hang out here. Now I've got to go back to my computer, but it's just such a incredibly gorgeous day out here at the site. This is when Flagstaff in northern Arizona is close to heaven on earth. So hopefully we will be able to welcome some of you back to Mars Hill in a very limited, kind of exclusive capacity as we all start to try to get back on with our lives as sensibly and safely, as responsibly as we can. And we're certainly going to try to do that here at Lowell, as well as around our community.
Great. Well, thank you so much, Jeff, for giving us this fantastic tour of the Lowell Discovery Telescope And everyone who's viewing, we'll be happy to see you next week for Cosmic Coffee.
Yep. See you next week.
All right. Bye-bye, everyone.
Bye.